everyone, and welcome back to the Deep Dive. You reached out asking for a deep dive into some foundational, yet incredibly complex technical areas.
Yeah, specifically the world of database administration and, well, the often tricky business of system integrations, especially those involving APIs.
Exactly. We've pulled together the source material you shared, everything from foundational guides to practical troubleshooting tips, and we're ready to really unpack it for you.
That's right. Our mission here in this deep dive is basically to guide you through these essential technical landscapes. We want to clearly define the jargon,
Yeah, highlight the common challenges.
and detail the troubleshooting techniques, drawing them straight from the sources. Think of us as your guides through the nuts and bolts of how data is managed and moved in modern IT.
So if you've ever wondered what a DBA actually does, or maybe why integrating two systems via an API feels like, well, navigating a minefield sometimes,
Then you're definitely in the right place.
let's jump right into the source material.
Okay, let's begin with the realm of database administration, the DBA.
Okay, so right away, the sources describe the DBA role as essentially being the custodians of organizational data.
Right.
They manage the database management systems, the DBMS itself.
Keepers of the digital vault, basically.
Keepers of the digital vault. I like that.
Precisely. And while that sounds kind of straightforward, the reality of the job, as painted by the sources, is actually pretty demanding. DBAs are expected to be experts on everything related to database technology.
Everything, wow.
Yeah, and often much more. It stretches into operating systems, networking, even application logic sometimes.
Which sounds like a recipe for long hours. And the sources confirm this, noting DBAs often average over 50 hours a week, including weekends.
That's what they say. And it's usually because of urgent performance issues popping up or, tight project deadlines requiring database changes, things that can't wait.
And there's this dynamic mentioned, the classic blame game.
Oh, yeah. The database often becomes the default suspect when application problems occur. The source captures this perfectly, saying the database is guilty until proven innocent.
Right. An application team facing an issue is far more likely to point to the database and say, it's slow, fix it.
Instead of maybe looking at their own code first or, other parts of the stack, it's just easier to blame the database sometimes.
Yeah, I've definitely seen that frustration from both sides. But okay, despite the pressure, the sources indicate that career prospects are actually pretty strong.
They do. The material points to employment growth projected much faster than average, citing a 20% increase expected between 2008 and 2018, and generally good compensation too.
So challenging work, definitely, but well compensated and in demand.
And a really interesting point the sources make is the unique perspective a DBA gains, because they manage that central data store, right? They often have visibility across multiple applications and systems that interact with that data.
Ah, so they see the bigger picture.
Exactly. They see the data flow and the dependencies from a broad cross-system vantage point that honestly few others in IT possess.
That wide view must be invaluable for diagnosing certain problems. Okay, so what are the fundamental responsibilities, the core pillars of this DBA role, according to the sources?
The sources break it down into several key areas. We should probably start with database design.
All right, let's unpack database design. What does that process actually look like?
Well, it's the process of taking a logical model of your data.
Okay, a logical model.
And translating it into a physical database design that's suitable for a specific DBMS, and then, implementing it. The sources explicitly state that a logical data model is a prerequisite. You absolutely must understand the structure and relationships of your data conceptually and logically before you even start thinking about how to store it physically in tables and files.
Gotcha. And the sources talk about different levels of these data models, conceptual, logical, and physical. Can you clarify what differentiates them?
Sure. The conceptual model is the highest level. It's very business-oriented and identifies the major entities, the core things or concepts your business data is about, like customer or order.
The big nouns.
Yeah, exactly. The sources advise keeping entity names simple, minimizing descriptive adjectives at this stage. It focuses on the major relationships, but doesn't necessarily document every single tiny detail.
Okay, so that's the big picture business view. Then comes the logical model.
Exactly. The logical model refines that conceptual model by adding significant detail. This is where you fully define the entities, specifying all the attributes for each one, along with their data types and lengths.
More detail.
Right. You identify all the candidate keys, the unique identifiers, and select the primary key for each entity. Foreign keys are rigorously defined to represent the relationships between entities, and you document the cardinality of these relationships.
Cardinality, like how many orders a customer can have.
Precisely. Like whether a customer can have 0, 1, or many orders. And the source is mentioned using normalization techniques at this stage to make sure the model is well structured and free from certain types of data redundancy issues.
Normalization. Okay, that's a key concept here. What exactly is it, and what's this first normal form, or 1NF, the sources discuss?
Normalization is a formal process, a technique really, for organizing data in a database. The main goals are to reduce redundancy and improve data integrity. It involves structuring your tables and columns according to a series of normal forms.
And 1NF is the first step.
It's the most basic, yeah. The sources define 1NF as eliminating repeating groups and also non-atomic data within an entity.
Okay, repeating groups. Non-atomic data. Could you walk us through the example from the sources to make that clearer? The student one.
Sure. So imagine you had a single student table and you tried to include multiple courses a student is enrolled in, maybe by adding columns like course 1, course 2, course 3.
Right, I've seen that attempted.
Or maybe even listing multiple course IDs in a single column, separated by commas or something. That violates 1NF. Those are repeating groups or non-atomic data.
So how do you fix it for 1NF?
To achieve 1NF, you'd need to create a separate table, maybe called student enrollment. And in that table, each row would contain just a student ID and a single course ID.
Ah, one enrollment per row.
Exactly. This ensures each piece of data, a student's enrollment in one specific course, is atomic and clearly belongs to a single record in that enrollment table. No messy lists.
Ah, I see. So 1NF is fundamentally about making sure each piece of data is unique and clearly belongs, prevents those lists within lists. That makes sense. Okay, so once the logical model is solid and normalized, then you move to the physical design.
That's right. That's where you implement the logical model for a specific DBMS. It involves making decisions about the physical characteristics of the database objects.
Like how tables and indexes are actually stored on disk.
Yeah, exactly that. And designing specific indexes to optimize access and mapping these database objects to the physical storage devices, all the concrete stuff.
The sources also mention referential constraints and check constraints in this phase related to integrity.
Yes, and these are critical database features for enforcing data integrity directly within the DBMS. Referential constraints are basically the physical implementation of the relationships you define logically.
So linking tables together properly.
Right. They ensure that foreign key values in a dependent table correctly reference primary key values in the parent table. The sources describe referential integrity rules, which dictate what the database does if you try to delete or update a parent row that has dependent children.
Like what happens to the child rows.
Yeah. Should it prevent the deletion? Should it cascade the delete to the children?
Mm-hmm.
Or maybe just set the foreign key in the child row to null? The constraint defines that behavior.
Okay. And check constraints, what are those?
Check constraints are rules you define on columns to enforce specific business rules or data integrity conditions. The source gives the example CHE, EmpNote 10.
So employee number must be greater than 10.
Right. This constraint prevents inserting or updating any row where the MO is 10 or less. And a key insight from the sources here is that enforcing integrity using these DBMS features like constraints and triggers is generally better than relying only on application code.
Why is that?
Because database-level constraints can't be easily bypassed. Someone using a different tool or direct SQL access still have to obey the constraint. Application code checks can sometimes be circumvented. So database constraints provide a more robust layer of data protection.
That's a crucial point. Integrity enforced at the source is always best. Okay, moving beyond design, the next core pillar mentioned is performance monitoring and tuning.
Ah, the constant battle for the DBA. Database performance is really all about optimizing the use of resources, CPU, memory, disk I/O, to maximize the workload processed, which we call throughput.
Get more done faster.
Exactly. And also minimize contention. That's when different processes are trying to access or modify the same resource at the same time, causing delays.
Okay. What are the common enemies of good database performance? According to the sources, what should you look out for?
Well, the sources place a heavy emphasis on issues related to poorly performing SQL queries and the use, or often the lack thereof, of indexes.
Indexes again, okay.
Yeah. The usual suspects include, first, table scans.
That sounds inefficient.
It's like reading an entire book just to find one sentence. The database reads every single row in a table because that doesn't have a more efficient way, like an index, to find the data it needs. This is incredibly slow on large tables.
Okay, what else?
Lack of appropriate indexes, maybe the necessary indexes just haven't been created. or improper indexing choices.
Mm.
The sources distinguish between just indexing by object, like putting an index on primary
It's
key,
the obvious stuff.
right, versus indexing by workload, creating indexes specifically designed to speed up the queries your applications actually run. Indexing by workload is highlighted as the optimal approach.
Makes sense. Support the real work.
Then there's not using available indexes. Sometimes indexes exist, but the query optimizer, maybe because of outdated statistics or a really complex query structure, just fails to use them effectively.
Frustrating.
Very. Also, outdated database statistics. The optimizer relies on stats about the data, how many rows, value distribution, etc., to choose the best access path. If these stats are old, it might make bad decisions.
Like using an old map.
Good analogy. Then, tables joined in a suboptimal order. The sequence matters a lot for performance. An inefficient SQL formulation, the sources point to certain subquery patterns, like some uses of exists or not exists, that can be really inefficient if not written carefully.
So the way you write the SQL itself matters.
Hugely. And finally, unnecessary sorting. Things like joins, order by, group by, union, distinct papers. These can all trigger really expensive sorting processes if the data isn't already available in the right order, ideally via an index.
So if you're debugging a slow application query, the big takeaway seems to be almost always look at how the database is trying to find the data. Is it doing a table scan? Is there a missing index? Is the SQL just clumsy?
Absolutely. Most database performance problems boil down to inefficient data access, which brings us right back to indexes. The sources call them alternate paths to data. The DBMS query optimizer uses them to quickly locate rows without scanning the whole table.
Okay, so what are the main reasons to build an index, besides just speeding up queries?
The sources list a few key purposes. One, obviously, is to enforce uniqueness for primary keys and other candidate keys. That's fundamental.
Right.
Two is to provide index-only access, sometimes called a covering index. If all the columns a query needs are in the index itself, the database might not even need to touch the base table data at all. That's super fast.
Nice. Avoids another lookup.
Exactly. And three, to minimize sorting. An index can provide data already in the order needed by an order by or group by, avoiding that expensive sort operation.
And what's clustering in the context of indexes? You mentioned that.
Right. Clustering is a performance optimization technique. It's where the database physically tries to store the data rows on disk in the same order as the values in a specific column, the cluster key.
So related rows are physically near each other.
Ideally, yes. When you query data in the cluster key order, the database can read contiguous blocks from disk, which significantly reduces I/O compared to jumping all over the disk. The sources do note, though, that because of insertions and updates, clustered tables might not always stay perfectly 100% clustered over time. Space issues can cause fragmentation.
Interesting trade-off. Now, you mentioned normalization for good design, but the sources also talk about denormalization for performance. That feels counterintuitive.
It is a deliberate trade-off, absolutely. Denormalization is when you intentionally deviate from the normalization rules. You usually do this by introducing some controlled redundancy.
Handing data back in that you took out.
Kind of, yeah, but strictly for the purpose of improving performance for specific critical queries. The sources list criteria for when this might make sense. Situations where, say, lots of important queries require joining many tables together frequently, or where you often process repeating groups that were normalized out.
So it's a calculated risk.
It is. You gain query speed, potentially, but you might make updates more complex, or you risk data inconsistency if it's not managed very carefully.
So this highlights a critical tension in database work. The ideal structure for integrity often clashes with the ideal structure for speed, and the key insight is sometimes you deliberately break the rules, but only for a proven performance gain, and always document it.
Exactly. And that documentation is absolutely crucial because it explains why the structure looks maybe a bit weird. It justifies the denormalization.
How do DBAs figure out why a query is slow in the first place?
They use tools provided by the DBMS to see the execution plan. That's the step-by-step plan the optimizer chose to run the query. The sources mention the explain statement in Oracle and DB2, which writes detailed plan info to a special table, often called plantable.
Okay.
And in SQL Server, there's show plan, which can give you textual or even graphical output of the plan. These tools reveal if table scans are happening, which indexes are being used or not used, how tables are being joined, and so on. It's like looking under the hood.
So tuning is mostly reactive. Wait for things to get slow, then use explain.
Not ideally, no. The sources really emphasize proactive performance management, designing performance considerations into applications right from the beginning of the development lifecycle.
Easier said than done, I bet.
Oh, definitely harder under time pressure, but it's significantly more effective than trying to bolt performance onto a poorly designed system later on.
And performance tuning isn't just about tweaking the database software itself, right? It's broader.
Correct. The sources point out that tuning involves the entire stack. You might need to look at the operating system configuration, the network latency, any middleware involved, and definitely the hardware infrastructure, CPU, RAM, disk speed.
And within the DBMS itself.
Within the DBMS, tuning includes careful choices during installation, setting configuration parameters correctly, and managing internal memory structures. Two key ones mentioned are the data cache, also called the buffer pool, and the procedure cache.
What role do those memory caches play? How do they help?
Well, the data cache, or buffer pool, is used to hold copies of frequently accessed data pages from disk right there in memory. Retrieving data from fast memory is way quicker than going to slow disk I/O every time.
Makes sense. Keep hot data close.
Exactly. And the procedure cache stores the optimized execution plans for SQL statements after the optimizer has figured out the best way to run them. So when the same SQL statement is executed again, the database can often just reuse the cached plan, saving the time and CPU cost of reoptimizing. This significantly boosts performance for queries that run over and over.
Okay, performance is clearly a huge ongoing task. Let's move to the next pillar, ensuring availability. The sources call this the holy grail for DBAs.
And for very good reason. As the sources state, if the data isn't available, the applications that depend on it simply can't function. In today's world of 247 e-business, downtime means lost revenue, damaged reputation, significant business impact.
Right. Those old batch windows where you could take databases offline for hours are mostly gone.
Increasingly rare, yeah. The demand for continuous or near continuous availability is paramount now.
So what kinds of things can actually knock a database offline?
Oh, a depressingly wide range of issues. The sources list things like hardware failures, servers dying, disk system outages, SAN failures, bad memory modules.
Physical stuff?
Yep. Then operating system crashes. Bugs or maybe resource issues within the DBMS software itself running out of memory or connections. Network problems cutting off access. Data corruption, which is a nasty one. Loss of individual database objects, like a critical table getting dropped accidentally, or even the complete loss of the entire database. And human error is explicitly mentioned DBAs making mistakes.
Oops.
Yeah. Security or authorization problems locking users out. And of course, both planned maintenance outages and totally unplanned failures. Lots of potential failure points.
That's a comprehensive list of potential nightmares. How did DBAs prepare for and mitigate these risks?
The sources outline several key strategies. A absolutely fundamental one is having a robust backup and recovery plan, which we definitely need to talk more about.
Okay. What else beyond backups?
Modern DBMSs and operating systems often have built-in high availability features. Clustering technology is a key approach mentioned.
Clustering. Tell me more.
Yeah, clustering involves linking multiple physical servers together so they act kind of like a single system and can share the database workload. If one server, one node in the cluster fails,
The others take over.
exactly, the workload could be automatically shifted to the remaining healthy servers. This improves both availability surviving a server failure and often scalability too by spreading the load. The sources give examples like Oracle RAC, which stands for Real Application Clusters, and IBM Sysplex on the mainframe side.
Okay. And standby databases, what are they?
A standby database, like Oracle's DataGuard for instance, is essentially a constantly updated copy of your primary database, often running at a separate location. It's kept ready, synchronized.
Ready to take over.
Yep. So if the primary database fails catastrophically, the standby can be quickly activated to become the new primary, minimizing downtime. The sources also mention the importance of non-disruptive utilities and online reorganization features.
Doing maintenance while things are running.
That's the idea. Some DBMSs allow critical maintenance tasks, like rebuilding indexes or reorganizing tables to reclaim space, to be performed while the database stays online and available to users. This avoids the need for planned downtime windows for those tasks. Load balancing is another related concept, distributing incoming connections or requests across multiple database instances to improve resilience and performance.
The sources also bring up different database architectures, like NoSQL, in the context of availability. How does that fit in?
Yeah, for certain specific use cases, particularly in the big data realm, like managing massive search indexes, serving high-traffic websites, handling streaming media, NoSQL databases are often chosen partly because of their inherent high availability and scalability
Yeah,
characteristics.
how are they different?
Well, the sources describe NoSQL systems as typically non-relational, often designed to be distributed across many commodity servers from the ground up. They tend to have flexible schemas, or sometimes no predefined schema at all, and they're built for scale-out. They might employ concepts like eventual consistency rather than the strict AC transaction guarantees of traditional relational databases as a trade-off to prioritize availability and performance in a highly distributed environment.
Interesting. A different set of trade-offs. And even something as basic as power supply is critical for availability.
Absolutely fundamental. The sources emphasize that DBA should ensure servers have redundant power supplies and are protected by uninterruptible power supply, or UPS, systems. A simple power glitch is actually a very common cause of server failure. Protection against that is foundational.
Okay, availability is clearly non-negotiable. Next up, database security and authorization, another critical area.
Definitely. The DBA is typically the primary guardian of database security, although this role can sometimes be shared with a dedicated security administration function in larger organizations. Database security requires specific expertise about the DBMS's own security mechanisms. It's often different from standard OS or network security.
What's the core task?
The core task is granting the right privileges, permissions to access or modify specific data or objects to the right users, and only the right privileges. Principle of least privilege.
Managing privileges for every single user individually sounds like a potential nightmare.
It can be, yeah. Which is why the sources highlight the use of authorization roles and groups. The terminology varies a bit between different database systems, but the concept is the same. You define a role or a group, assign a set of necessary privileges to that role or group, and then you just grant the role or group to the users who need those permissions.
Much simpler. Manage the role, not hundreds of users.
Exactly. It vastly simplifies administration compared to managing permissions user by user. The sources also offer some basic but important guidance on password policies for users. Make them difficult to guess. Don't use personal info, standard stuff, but still important.
SQL injection is called out specifically as a significant threat. What is it, and what's the key prevention method mentioned?
Right. SQL injection is a really nasty technique where an attacker injects malicious SQL code into application input fields like a search box or a login form. If the application doesn't properly sanitize or validate that input before using it to build a database query.
The bad code gets run by the database.
Precisely. That injected code can then be executed by the database, potentially leading to unauthorized data access, data modification, deletion, or even taking control of the database server in some cases is a major vulnerability. But the sources state emphatically that with foreknowledge and proper procedures, SQL injection can be prevented.
Okay, so how do you prevent it? What's the core strategy?
The primary defense mentioned in the sources is using static SQL instead of dynamic SQL, especially for hard-coded database access within applications.
Static versus dynamic.
Yeah. Static SQL is SQL code that's fully written and pre-compiled as part of the application code. Its structure is fixed. Dynamic SQL, on the other hand, is constructed or modified by the application at runtime, often incorporating user input directly into the query string. That's where the danger lies. If user input isn't handled very carefully, it can alter the SQL command in unintended ways. Using static SQL or parameterized queries, which achieve a similar safety goal for operations that don't strictly need to be dynamic, effectively removes the injection vector.
Got it. Avoid building SQL strings with user input. The sources also list some common mistakes that compromise database security.
Yes, granting excessive authority is a big one, like giving the highest level of privilege, SYSADM or DBA role, basically root access to the DBMS, to system accounts like a job scheduler that probably only needs very specific permissions. That's just asking for trouble if that account is compromised.
What else?
Embedding clear text passwords directly in database utility scripts or batch job files. That's another major no-no. Anyone who can read the script or see the job definition can steal the password.
And security isn't just confined within the database software itself, is it?
Correct. The sources note that DBAs often require high-level operating system privileges, sometimes even root or administrator access on the server itself to perform certain maintenance, installation, or configuration tasks. This means there needs to be close collaboration and trust between the DBAs and the system administrators. OS-level security needs to be properly managed to protect the underlying platform without preventing the DBA from doing their essential job.
It's all connected. And compliance with regulations like GDPR, CCPA, DPA comes up again here in the security context.
Yes, absolutely. Regulatory compliance is a huge driver for security practices. The sources emphasize that complying with these regulations is a complex, multidisciplinary effort. It requires collaboration between business folks, IT teams, and legal counsel. Organizations need to meticulously map their data elements to specific regulatory requirements to ensure data is handled compliantly, how it's accessed, stored, secured, retained, and deleted throughout its entire lifecycle.
Okay, backtracking slightly to another absolutely critical pillar, backup and recovery. You touched on it for availability, but the sources dedicate significant detail specifically to this.
Yeah, it's utterly foundational. As the sources bluntly put it, things break. Your ability to recover from any kind of failure, hardware, software, human error, data corruption, whether it impacts availability, data integrity, or just usability, is entirely dependent on having a well-defined, well-tested backup and recovery strategy. No plan, no recovery.
So what does the backup part typically involve?
Backup fundamentally involves creating consistent copies of your database data. This is usually done using specialized utilities provided by the DBMS itself. These utilities create what are often called image copies of database structures, like table spaces or data files. The sources mention utility names like copy, backup, DMP, export. While you can sometimes rely on simple OS file copies for very basic setups, the sources generally recommend using the DBMS-aware utilities because they understand database consistency better.
And if you back up data tables, you need to think about indexes too.
Yes, good point. The sources note that if you back up data table spaces, you should ideally back up their associated index table spaces concurrently, or at least have a plan to rebuild the indexes as part of the recovery process. Otherwise, your recovered data might be missing its performance-critical indexes.
And the transaction log is mentioned as absolutely critical for recovery. Why is it so important?
It is perhaps the most critical component for most types of recovery, especially point-in-time recovery. The transaction log, sometimes just called the database log, records every single change made to the database, every insert, update, delete operation. These log records are essential for recovering data after a failure.
How are they used?
They allow you to roll forward transactions that happened after your last backup was taken, bringing the restored database up to a specific point in time. Or they allow you to roll back transactions that were incomplete when a crash happened. The sources really stress the importance of log archiving and backup. If you don't archive or back up your transaction logs properly, you might lose the ability to recover any changes made since your last full backup. That could be hours or even days of data loss. They strongly recommend running with dual active logging as a minimum safeguard, maintaining 2 identical copies of the active log file on separate disks.
You mentioned consistency for backups earlier. What does that mean in practice? How do you get a consistent backup?
Consistency means capturing the data at a specific moment in time when it's stable, essentially a snapshot where no updates are in progress on the objects being backed up. This is often achieved by momentarily pausing or quiescing activity on those specific database objects while the backup utility reads them. A consistent backup is crucial because it provides a reliable, known starting point for recovery. If you try to recover from an inconsistent backup, you might not be able to reliably apply the transaction logs afterwards.
Okay, so let's say something does go wrong. What are the general steps for recovery that the sources outline?
The sources lay out a pretty systematic process. First, identify the failure. Is it an obvious outage or something more subtle like corrupted data or damage control file?
Okay.
Second, analyze the situation. This is often the most time-consuming part. You need to figure out the cause, the type of failure, the scope, what's affected, and the impact. What broke? How badly? What data is involved?
Diagnose.
Exactly. Third, select the recovery method. Based on your analysis and what backups and logs you have available, are you doing a full restore, a point-in-time recovery, just recovering one damaged table?
Choose the right tool.
Right. Fourth, execute the recovery. Run the necessary DBMS utilities or recovery scripts. Fifth, verify the recovery. This is critical. Don't just assume it worked. Check that the data is consistent, accessible, and the system is behaving as expected. Test it.
Trust but verify.
Definitely. And sixth, document the problem and the solution. Record what happened, why it happened, how you fixed it, and any lessons learned. This helps improve procedures and hopefully prevent it from happening again.
Makes sense. And point in time, PIT recovery, you mentioned that.
PIT recovery is a very common requirement. It's where you need to restore the database, or maybe just specific objects, back to a precise, consistent point in time before something bad happened, like right before a user accidentally deleted a bunch of critical data, or before a faulty batch job corrupted things.
How does that work?
The typical process involves restoring an older image copy backup. one taken before the problem occurred, and then applying transactions from the archived database logs, rolling forward step by step, stopping precisely at the desired recovery point in time.
Sounds complex. What are some best practices the sources suggest for backup and recovery?
Several key practices are highlighted. First and foremost, test your backups. You absolutely must test that you can actually recover successfully from your image copy backups before a real disaster strikes. A backup you can't restore from is completely useless.
Practice the recovery drill.
Exactly. Second, automate procedures. Automating backup processes and even parts of the recovery process where possible minimizes the risk of human error, especially during a stressful outage, and speeds things up. Third, design databases with minimal dependencies between objects where feasible. Simpler structures are generally easier and faster to recover. And fourth, grade database objects. Assess your data objects based on their criticality. How vital is this data to the business? And their volatility. How often does it change? This grading helps you determine the appropriate backup frequency for each object. Critical, highly volatile data probably needs more frequent backups than static lookup tables.
That makes sense. Focus backup efforts where they matter most. Disaster recovery, DR, is mentioned as being distinct from standard backup and recovery. How so?
Yeah, DR is about planning for the really big catastrophes. Think loss of an entire data center due to a fire, flood, earthquake, or other major incident. It's a much broader plan than just recovering from a server failure. It typically involves multiple IT disciplines, business continuity teams, not just the DBAs.
Site-level survival.
Right. The sources strongly emphasize having a formal written DR plan and, absolutely critically, regularly testing that plan. An untested DR plan is often just wishful thinking. DR backup strategies might involve backing up entire disk volumes, shipping image copies or tapes off-site, or replicating data electronically to a remote DR site. The key is having backups off-site, physically separate and secure, far enough away from the primary site to survive a regional disaster.
Got it. Recovery is fixing local failures. DR is surviving site-level destruction. Makes sense. Governance and regulatory compliance come up again here, too, briefly.
Yes, just reinforcing the point that adherence to regulations like GDPR, CCPA, IPA impacts your backup strategies, your data retention policies, how long you keep backups, and overall data management governance. It requires that ongoing collaboration across teams to ensure your entire data lifecycle management aligns with legal requirements.
Okay. And finally, for the DBA pillars, the sources mention metadata management. What's that about?
Metadata is essentially data about data. The sources describe it as providing the necessary context to understand your data, transforming raw bits and bytes into meaningful information. A strong metadata management strategy is vital for an organization to truly understand and measure the value of its information assets.
Where is this metadata stored?
Repositories and data dictionaries are the centralized systems mentioned for storing and managing this metadata. They act as a kind of single source of truth about the organization's data landscape, what data exists, what it means, where it comes from, how it's used.
Wow, okay. That's a really comprehensive overview of the DBA world. It's clearly much, much more than just writing SQL queries.
It really is. It's a multifaceted and absolutely critical role in any organization that relies on data, which is pretty much every organization these days.
Right. Now let's shift gears to the other major area covered in the sources, navigating the web of integrations, focusing particularly on troubleshooting APIs and data flow.
Yeah, this feels like where the rubber really meets the road in modern systems, doesn't it? Getting all these different pieces of software, often from different vendors, to actually talk to each other reliably.
Definitely. What are the big challenges the sources point to in this world of integrations? Where do things typically go wrong?
Several key areas stand out as particularly difficult and persistent. First, there's data mapping, transformation, and consistency. The sources call this one of the most persistent challenges in integration.
Why is just converting data between systems such a headache? Seems like it should be straightforward.
You'd think so, but every system often has its own unique data formats. The sources mention common ones like CSV, Excel, JSON. Each system has its own schema, right? How the data is structured internally, and maybe even more tricky, different semantic interpretations.
Meaning the same word means different things?
Exactly. The same field name, like customer aid, might mean slightly different things or have different formatting rules or constraints in different systems. Converting data accurately and consistently between these diverse structures is complex and very error-prone. Mistakes here can lead to data loss, data corruption, or just inaccurate information propagating silently throughout your connected systems. And dealing with unstructured data, of course, makes this whole problem even harder.
So ensuring customer aid from System A cleanly maps to client identifier in System B and means the same thing is harder than it looks. Okay. What's the next major hurdle according to the sources?
Security and compliance. This is huge. The sources emphatically state that security is paramount. Poorly designed integrations essentially create new doors and windows into your systems, new potential vulnerability points for unauthorized access, data breaches, and leaks. You absolutely have to evaluate data protection at every single point where systems connect.
And specific security issues come up frequently with integrations, especially APIs.
Oh yes, authentication and authorization failures are very common API integration issues. The sources list problems like getting HTTP 401 unauthorized errors, which usually means your authentication failed, maybe an invalid API key or password. Or you might get a 403 forbidden error, which means you did authenticate successfully, but your identity doesn't have permission for the specific action you're trying to perform.
Need the right permissions.
Right. The sources even give specific examples like needing detection access for a silence integration or needing the grant read log permission for a Cisco Duo integration. Expired credentials, like an API access token that's only valid for an hour running out, are another really frequent cause of failure.
And compliance comes back into play here too.
Definitely. Beyond just the specific API security, the integrated systems, viewed as a whole, must collectively comply with regulations like GDPR, CCPA, IAPI throughout the entire data flow and integration lifecycle. This adds significant complexity, ensuring data privacy and security rules are followed end to end.
Okay. And the third big challenge area.
Scalability and flexibility. Integrated systems need to be able to handle increasing data volumes and transaction loads as the business grows. The sources warn that integration methods or platforms that don't scale well can quickly become performance bottlenecks, leading to slowdowns, timeouts, and errors under heavy load.
So the integration itself becomes the weak link?
It can, yeah. Furthermore, integration solutions need to be flexible enough to adapt to evolving business needs or changes in the connected systems. If they're too rigid, they'll require costly re-engineering and ongoing maintenance down the line, becoming technical debt.
It sounds like a lot of complex technical plate spinning, but the sources also dedicate significant space to the people and process side of integration problems. How does that fit in?
And they argue quite strongly that these non-technical factors often exacerbate the technical difficulties. For example, unclear requirements from the business side make accurate data mapping or effective API management nearly impossible for the technical team.
Garbage in, garbage out.
Basically, a lack of necessary expertise within the integration team can cripple efforts to design for robust security and scalability from the start. And common project pitfalls like scope creep, oversimplification of the problem, oh, just connect A to B, it's easy, or a lack of clear ownership and accountability for the end-to-end integrated system often stem from organizations just fundamentally underestimating the true complexity involved in integration projects.
So the takeaway is that viewing integrations as just another IT task, something to hand off to the techies, is a big mistake.
According to the sources, yes, absolutely. They argue for elevating integrations to the level of strategic business initiatives. They need cross-functional ownership involving business stakeholders and IT-strong executive sponsorship and rigorous project management oversight, just like any other major business project. Shifting this perspective can help address many of those people and process pitfalls.
Okay, let's move into troubleshooting. The sources note that integration failures don't always show up as obvious error messages. Their symptoms can be wider.
They really can. Failures aren't always just technical glitches, like a 500 error. Their impacts can manifest in sneakier ways. Maybe operational inefficiencies because data isn't flowing correctly, flawed business decisions being made based on bad or incomplete integrated data, decreased customer satisfaction due to delays or errors, and even direct financial losses. Recognizing these varied symptoms across the business is crucial for early identification that, hey, maybe something is wrong with one of our integrations.
And the troubleshooting process itself, the sources describe it as systematic.
Yeah, it's framed not just as reactive fixing, put out the fire, but as an iterative learning process. The steps will sound familiar. They mirror good problem solving in general. First, identify the failure symptom. Second, analyze to find the root cause. Third, choose the best method to fix it. Fourth, implement the fix. Fifth, verify that the fix actually worked. Sixth, document the problem and the solution. And seventh, importantly, adjust processes or designs based on the lessons learned. This last step is what turns troubleshooting into continuous improvement, hopefully preventing the same failure again.
Isolation is presented as a fundamental troubleshooting technique, especially for complex systems.
Absolutely critical. When you have multiple systems interconnected, figuring out where the fault lies can be really hard. Isolation is basically a divide and conquer strategy. Techniques like mocking or stubbing out external dependencies.
What does that mean, mocking or stubbing?
It means creating a temporary, fake version of an external system or API that your system depends on. This fake version just provides predictable responses, allowing you to test your system or a specific part of the integration flow in isolation without needing the real external system to be available or behaving perfectly. It helps you pinpoint whether the fault lies in your code, the external system's actual behavior, or the connection between them. It makes the problem much more manageable to diagnose.
Makes sense. Break the chain to test the links. Okay, let's delve into some specific integration issues and troubleshooting techniques detailed in the sources. Starting with API integration issues, since APIs are so central.
Right. APIs are crucial for modern integrations, but yeah, they bring their own set of common challenges. Things like managing authentication correctly, handling different API versions gracefully, respecting rate limits imposed by the provider, and dealing with dependencies on the stability and performance of that external API service.
We touched on authentication and authorization failures already. Just to recap, what's the key difference again?
Sure. Authentication is about verifying who you are, proving your identity, usually with credentials like an API key, username, password, or a token. Authorization is about verifying what you are allowed to do now that the system knows who you are, checking your permissions for the specific action you're requesting.
Got it. Identity versus permissions.
Exactly. Common failures here are things like sending invalid credentials, leading to 401 unauthorized, having insufficient permissions for the action you're attempting, leading to 403 forbidden, or using credentials that have expired, like an access token that's no longer valid.
And API errors are often signaled by those HTTP status codes. Can you quickly run through the common ones the sources mention again, the 400s and 500s?
HTTP status codes are the standard way APIs communicate the outcome of a request. The sources highlight. 4xx codes, which generally mean there's a client error. Something is likely wrong with the request your system sent.
My fault.
Probably, yeah. Common ones are 400 pounds. Bad request. The request itself was malformed, invalid syntax, missing parameters, etc. 401, unauthorized. Your authentication failed. Invalid credentials, missing token. 403, forbidden. You authenticated okay, but your identity doesn't have permission for that specific action or resource.
Right.
404, not found. The specific API endpoint or resource you requested doesn't exist. 429, too many requests. You've hit the API provider's rate limit. Slow down.
Okay. And the 5SX codes?
5xx codes mean there's a server error. The problem is likely on the API provider side, not your fault.
Their fault.
Usually. Common ones are 500 internal server error, a generic catch-all. Something unexpected went wrong on their server. Not very specific, unfortunately. 503 service unavailable. The server is temporarily unable to handle the request. Maybe it's overloaded, down for maintenance, etc. Try again later.
So how do you start troubleshooting when you get one of these specific API error codes?
The sources recommend a few steps. First, always consult the API provider's documentation. They often have specific meanings or additional details associated with certain error codes that go beyond the standard HTTP definition.
Like the manual.
Always. Second, validate the structure of your request meticulously. Check the URL, the HTTP method, DT, POST-D, etc. The headers, especially authentication headers, the request body format, usually valid JSON, required parameters. Even a small typo can cause a 400 error. Details matter. Absolutely. Third, use tools like Postman or the curl command line tool to try and send the exact same request outside of your application code. If it fails in Postman or curl with the same error, the issue is almost certainly with the request itself or the API, not a bug in your application's logic for sending the request. It helps isolate the problem.
Good tip. The sources also detail different methods APIs use for authentication and authorization.
Yes, they cover some common mechanisms you'll encounter. API keys. These are usually simple token strings. You often pass them in a request header like authorization, bearer key, or maybe a custom header like xAPI key.key. They're relatively easy to implement, but must be kept confidential, just like a password, because possessing the key often grants access. They can usually be revoked by the provider if compromised. OAuth 2.0. This is a widely used framework for delegated authorization. It's more complex than simple API keys. It allows a user to grant your application permission to access their data on another service, like Google or Salesforce, without you ever handling their actual password. It involves multiple steps, redirects, and ultimately results in your application getting an access token. This token represents the user's permission for specific actions defined by scopes and is passed in subsequent API requests, usually as a bearer token. JSON Web Tokens, JWT. These are often used within OAuth 2.0 flows as the format for the access tokens, specifically as bearer tokens. A JWT is a contact URL safe string that contains claims, pieces of information like the user ID, their roles or permissions, the token issuer, the intended audience, your API, and an expiration time. Crucially, a JWT is digitally signed by the issuer.
Why is the signature important?
The signature allows the receiving API, your API, or the one you're calling, to verify that the token hasn't been tampered with, and that it was actually issued by a trusted authority. The source is specifically warned that the algorithm header in a JWT should never be set to none, meaning no signature verification. That's insecure. Consuming applications must validate the token's signature and also check crucial claims like the issuer, audience AUD, and especially the expiration time to ensure the token is still valid and intended for them.
Okay, lots to check with JWTs. What about general security best practices when building or using APIs?
Adhering to security guidelines like the OWASP API Security Top 10 is highlighted as crucial. This list covers common vulnerabilities like broken object-level authorization, a big one where user A can accidentally access user B's data because the API doesn't check ownership properly, broken authentication, excessive data exposure, lack of resources and rate limiting, etc. Following these helps prevent common attacks.
So OWASP DIB's key.
Yes. And the sources also remind us that while using HTTPS encrypts the data in transit, protecting it from eavesdropping on the network, it doesn't protect against vulnerabilities in the API's application logic itself. So you still need essential practices like robust input validation, don't trust data coming in, secure configuration of the API server and underlying infrastructure, and implementing rate limiting to prevent denial of service attacks or abuse.
Okay. API versioning is mentioned as another practical challenge for integrations. Why?
Because APIs inevitably evolve over time. The provider needs to add features, fix bugs, maybe change data structures. Versioning allows the API provider to introduce these changes, potentially breaking changes, without immediately breaking all the existing integrations that rely on the older version.
How is versioning typically done?
Common strategies mentioned in the sources include putting the version number directly in the URI path, like a P1 users versus a P few users, including it as a query parameter, like a psers.version2, or specifying it in a custom HTTP request header, like accept.application vnd.company.v2 plus JSON, or XAPI version 2.0.
Any best practices for handling versioning?
Yeah, the sources suggest providers should try to maintain backward compatibility for older versions for a reasonable period. Provide clear documentation and change logs detailing what's different in each version, and have a clear deprecation policy, giving consumers plenty of advance notice before an older version is eventually retired. As a consumer, you need to be aware of the version you're using and plan for upgrades.
Right, and handling rate limiting is essential for reliable integrations, you mentioned.
Absolutely vital. Many, if not most, public APIs impose limits on how many requests a single client, identified by API key or user token, can make within a certain time window, maybe per second, per hour, or per day. These limits vary wildly between systems. Salesforce is mentioned in the sources as one example that has specific limits you need to be aware of.
What happens if you hit the limit?
You'll typically start getting those 429 too many requests error responses, and your integration stops working until the next time window starts.
So how do you deal with rate limits effectively?
Strategies include, first, monitoring your API usage. Know how close you are to the limits. Tools like Salesforce's API usage notifications can help. Second, implementing rate limiting strategies in your own client code. Maybe using algorithms like Token Bucket or Leaky Bucket to automatically slow down or queue your outgoing requests so you don't exceed the limit. Third, optimizing your API calls. Retrieve only the data you actually need. Use bulk batch endpoints if the API provides them to perform multiple operations in a single request. Fourth, caching data locally where appropriate to avoid making repeated API calls for data that doesn't change often.
Okay, good strategies. Going back to data issues for a moment, the sources revisit data-centric challenges even when you're using nice structured APIs.
Yes, because even if the API provides data in a clean format like JSON, the quality and consistency of the source data being sent or retrieved still matter hugely. The sources reiterate the importance of data profiling, understanding the characteristics, quality, and completeness of your source data before you try to integrate it. And data cleansing, fixing inconsistencies, errors, standardizing formats, and handling missing values in the source data before it even enters the integration flow.
And validation on the receiving end.
Right. Implementing data validation rules, perhaps using features available in the target system. The sources mentioned Salesforce validation rules as an example, helps ensure that the data meets required business rules, standards, and formats before it gets saved into the target system, acting as a final quality gatekeeper.
What about simple network connectivity issues? Can they be the culprit?
Absolutely. The sources list network problems as a potential, sometimes obvious cause of integration failures. If your system simply can't reach the API endpoint server due to firewall rules, DNS problems, routing issues, or general network instability, the integration will fail. Error messages like "problem with reaching the third-party service" often point in this direction.
Simple but important to check. And performance bottlenecks and security vulnerabilities also come up again here, specifically in the context of integration issues themselves.
Yes, these can be problems within the integration layer itself, or perhaps exacerbated by the way the integration works. Performance issues in integration might be identified by tracking slow response times in performance logs for the integration process.
Hmm.
Security vulnerabilities might be specific to the integration code or configuration, perhaps detected through security logs showing suspicious activity related to the integration flows.
This leads us naturally to a really critical set of tools for troubleshooting all these integration problems: the power of logs and metrics.
Absolutely vital. You really can't troubleshoot complex integrations effectively without good logging and metrics. Logs provide that detailed, step-by-step record of exactly what happened during an integration attempt, allowing you to backtrack and diagnose where things went wrong.
What kinds of logs are most useful here?
The sources list several key types. Access logs. These record every API request received or sent. They typically include details like who the caller was, which endpoint was hit, the timestamp, the HTTP status code returned, and how long the request took to process. Great for identifying as issues are specific to certain users, geographical regions, or particular API endpoints. Error logs. These specifically document exceptions and failures that occur within the integration code or API handling. They should provide error codes, detailed messages, and often stacked traces to help pinpoint the exact source of the problem in the code. Severity levels, like error, warn, info, help prioritize which issues to tackle first. Performance logs. These track metrics like response times for different parts of the integration flow or resource consumption, CPU, memory. They help you identify bottlenecks, which steps are taking too long. Security logs. These record important security-related events, like authentication attempts, successes and failures, authorization checks, changes to permissions, and any detected potential security threats, essential for investigating breaches or unauthorized access attempts.
Okay, so having these logs is step one. But just having logs isn't enough, especially when a single transaction might cross multiple systems, right?
Precisely. That's where the sources strongly emphasize the critical need for log centralization and standardization. In a typical modern integration, a single business transaction, say, processing an order might trigger calls across several different microservices or systems. Each of those systems might generate its own logs, possibly in completely different formats.
Making it impossible to follow the trail.
Exactly. Log centralization means collecting all these disparate logs into a single searchable platform. Standardization, or normalization, involves parsing these logs and converting them into a consistent format, maybe with common field names for things like timestamp, user ID, service name, error code, etc. This makes searching and analysis across logs from different systems much easier.
And how do you link log entries from different systems that belong to the same original transaction?
A key technique mentioned for this is using correlation IDs. This involves generating a unique identifier for each initial incoming request, and then ensuring that this ID is passed along consistently in the headers or messages as the request propagates through all the downstream services involved in handling that transaction. Each service includes this correlation ID in its log entries. Then, in your centralized logging system, you can easily filter for that specific ID to see the complete end-to-end trace of that single transaction across all involved services. It's incredibly powerful for debugging distributed systems.
What tools are typically used for this kind of log management and analysis?
The sources list several common log management tools. Signav's, the ELK stack, which combines Elasticsearch for search, Logstash for processing, and Kibana for visualization, Graylog, FluentD or FluentBit for log collection, and Spunk, which is a popular commercial option. These platforms specialize in aggregating logs from numerous sources, providing powerful searching and analysis capabilities, and creating dashboards and visualizations to help you spot trends, anomalies, or specific issues.
Okay, logs give you the details. What about API metrics? How do they complement logs?
Metrics give you the quantitative overview, the big picture trends. They track key performance indicators, KPIs, over time. Common API metrics mentioned include average response time, total throughput, often measured in requests per second, error rate, the percentage of requests that result in errors, often broken down by status code like 4xx versus 5xx, and overall availability or uptime.
How are metrics different from logs?
Metrics are typically numerical time series data points, whereas logs are usually structured or unstructured text events. Metrics are great for aggregation. You can easily calculate averages, sums, percentiles over time periods. You can also segment metrics by different dimensions, like tracking the average response time per specific API endpoint or the error rate per client application. They help you see high-level trends and spot deviations from normal behavior quickly. Is our overall error rate spiking, or is response time degrading?
Application performance monitoring APM tools are also mentioned. How do they fit in?
APM tools often combine logs, metrics, and distributed tracing, which relies on those correlation IDs, to provide real-time visibility into the health, performance, and availability of your entire application stack, including the integrations. They collect all this telemetry data automatically and visualize it, often showing dependencies between different services and highlighting performance bottlenecks or errors right within the application code or infrastructure components that might be causing integration problems. They give a deeper, more application-centric view than just looking at raw logs or infrastructure metrics alone.
So how do you actually put all this together, logs, metrics, APM, to solve a real integration problem?
The real power comes from correlation. You start with a symptom. Maybe metrics show a spike in 503 errors for a specific API endpoint. APM might flag this too. You then dive into the centralized logs, filtering by that endpoint at the time frame of the spike. You look for corresponding error messages. Maybe you use the correlation IDs from failed requests logged by the caller to trace those specific requests through the downstream services involved.
Following the breadcrumbs.
Exactly. By analyzing the logs from the different systems involved, linked together by correlation IDs, and comparing this detailed information with the broader trends shown by performance and error metrics, you can usually pinpoint the root cause. Is the API itself failing with 500 errors? Are requests timing out because a downstream database is slow, performance logs metrics? Are you hitting a rate limit, 429 error? Is it a data validation error happening somewhere in the flow? This correlated analysis across different data sources is the core of effective integration troubleshooting.
And good logging practices make this easier.
Immensely. Implementing structured logging, for example, logging in JSON format rather than plain text, with consistent field names, accurate timestamps, always including correlation IDs, and log in relevant context like request response payloads, being careful not to log sensitive data, makes this analysis much more efficient and powerful. This analysis then directly informs your incident response and remediation process, allowing you to quickly understand the problem, implement a fix, and minimize the business impact.
Okay, let's look at a specific integration pattern mentioned in the sources. Webhooks. How do they differ from typical API calls, and what are the common troubleshooting points?
Right. The sources explain webhooks as being fundamentally different from the usual request-response API pattern. Webhooks are an event-driven push mechanism. This is contrasted with polling, which is a request-driven poll.
Push versus pull.
Yeah. With polling, your system has to repeatedly ask an external service, do you have anything new for me? Do you have anything new now? Over and over again. With webhooks, the external service, the provider, automatically pushes data to your system, the consumer, via an HTTP request, but only when a specific event actually occurs in their system that you're interested in, like an order status changing or a new contact being created.
So more efficient.
Generally, yes. The sources note webhooks are usually much more efficient and scalable for receiving timely updates because they eliminate all those unnecessary polling requests when there's no new data to report. You only get contacted when something actually happens.
How do they work mechanically? What's the flow?
Typically, when an event you subscribe to happens in the provider system, it triggers the provider to generate a payload, often a JSON object containing details about the event. The provider then sends this payload as an HTTP POC request to a specific URL on your system that you pre-configured with them, your webhook consumer endpoint. Your system receives this incoming HTTP request and needs to process the payload.
What's the tricky part for the consumer, the system receiving the webhook?
A key characteristic mentioned is the fire and forget nature from the provider's perspective. They send the webhook request and expect a relatively swift acknowledgement from your consumer endpoint, typically an HTTP 200 OK status code, usually within just a few seconds. They don't want to wait around while you do complex processing.
What happens if the consumer takes too long to respond with that 200 OK?
If your system tries to do lengthy, synchronous processing of the webhook payload before sending back that 200 OK acknowledgement, the webhook provider might time out, waiting for the response. When that happens, the provider often assumes the delivery failed and will try sending the exact same webhook request again, potentially multiple times according to their retry policy. This can lead to duplicate processing on your end if you're not careful.
So how should consumers handle potentially long-running processing triggered by a webhook?
The sources highlight that for reliable and scalable webhook consumption, the best practice is for your consumer endpoint to do minimal work synchronously. It should validate the request quickly, maybe acknowledge it immediately by sending the 200 OK back to the provider, and then place the actual webhook payload onto an asynchronous message queue, like Amazon SQS or RabbitMQ, which are mentioned as examples. Separate background worker processes can then pick messages off the queue and do the heavy lifting, the actual processing, without holding up the initial acknowledgement to the provider.
Adds complexity but makes it more robust.
Exactly. It decouples the acknowledgement from the processing, preventing timeouts, and handling retries more gracefully.
Is there usually a security step involved when you first set up a webhook subscription?
Yes, some providers use what's called a handshake or validation process as a security measure. When you first register your consumer URL, the provider might immediately send a special initial request to it, perhaps an HTTP GET or options request containing a challenge token. Your consumer endpoint must respond in a specific way documented by the provider, often by echoing back the challenge token to confirm that the URL is valid, reachable, and actually willing to receive webhooks from that provider. This helps prevent misconfigured subscriptions or someone maliciously pointing webhooks at an unsuspecting server.
Makes sense. And other security considerations when dealing with webhooks.
Several important ones are mentioned. Always use HTTPS for your consumer URL to encrypt the payload data in transit. Be cautious about sending highly sensitive data directly in the webhook payload. It might be safer for the provider to just send an identifier, like an order ID, in the webhook, and then have your consumer system securely retrieve the full sensitive details via a separate authenticated API callback to the provider. Practice secure logging. Be careful not to log sensitive payload data inadvertently. Mitigate insecure endpoint exposure. Your webhook consumer URL is publicly accessible. You need ways to ensure only the legitimate provider can actually send requests to it. Common methods include validating request signatures, where the provider signs the payload with a shared secret, checking source IP addresses, IP whitelisting, or using mutual TLS and TLS for stronger authentication. Avoid returning verbose error messages from your consumer endpoint if something goes wrong during processing, as this could leak internal system details to potential attackers. Return generic error codes instead.
Okay, lots to think about with webhooks, too. The sources use the Salesforce REST API as a concrete example of API integration. Can you elaborate on that?
Yes, it serves as a good practical case study. The Salesforce REST API essentially allows external applications to interact programmatically with a Salesforce organization. You can use it to access data, query accounts, contacts, opportunities, etc., create new records, update existing ones, delete records, and even invoke custom Salesforce logic like Apex code remotely.
What are the benefits of using it?
The benefits listed include enabling real-time data synchronization between Salesforce and other systems, automating business workflows that span multiple applications, integrating Salesforce with various third-party services, improving overall data accuracy by reducing manual data entry, and offering a lot of flexibility in how external systems can leverage Salesforce data and functionality.
And its structure follows standard REST principles, as you mentioned before.
Exactly. It's based on standard REST concepts. You use standard HTTP methods. Get for retrieving, post for creating, patch H or put for updating, delete for deleting, applied to specific resources, which correspond to Salesforce objects like account or contact, identified by unique URIs. You typically send data in the request payload, usually JSON format, and receive back standard HTTP responses containing status codes and response payloads, also usually JSON.
Is authentication complex?
It typically uses OAuth 2.0. The sources provide a Python code example that illustrates the common flow. First, your application needs to go through an OAuth flow to authenticate and obtain an access token. Then you include that access token, usually as a bearer token in the authorization header, in all subsequent API requests to actually query or manipulate Salesforce data.
And managing those Salesforce API limits is reiterated as being crucial for success.
Absolutely critical. The sources explicitly mention this again in the Salesforce context. You must understand and manage the specific API limits imposed by Salesforce. They have both daily request limits based on your license type and edition, as well as concurrent request limits. Failing to do so is a very common cause of Salesforce integration failures.
So the advice is?
Review Salesforce's documentation carefully to understand the limits that apply to your organization. Actively monitor your org's API usage. Salesforce provides tools like API usage notifications for this, and implement those strategies we discussed earlier. Intelligent caching, using batch processing APIs where available. Salesforce has bulk APIs for this, and potentially implementing rate limiting or queuing in your own integration code to stay within those limits and ensure your integration remains reliable.
Okay. Now, the sources also briefly mentioned HubSpot as another system people integrate with.
Yes, HubSpot is noted as a popular CRM and marketing automation platform that organizations frequently integrate with, much like Salesforce. It definitely comes up as an integration target. But the provided source material that we're working from for this deep dive does not contain any specific technical details about how to implement or troubleshoot integrations specifically with HubSpot. There's no mention of its API specifics, authentication methods, common debugging issues, etc. in the material we reviewed.
So while it's acknowledged as an integration possibility, we can't really go into the technical weeds on HubSpot based on these sources.
Correct. We have to stick to what the sources actually provide details on, and for HubSpot, those details aren't present in this particular set of materials.
Fair enough. We stick to the source evidence. Finally, there's a very brief note tucked away about PHP debugging. What did the sources say there?
Right, it was just a quick mention, likely in the context of integrating with or working on applications like CivCRM, which are written in PHP. The point made was that PHP code often runs as part of a web server process, potentially even on a remote machine. This makes debugging a bit different than debugging a simple local script. It typically requires using a network debugger that can connect from your development machine to the running PHP process on the web server. The sources specifically recommended Xdebug as a popular and effective tool for debugging PHP code in this kind of web server environment.
Okay, good practical tip for PHP devs. Wow. We have covered a massive amount of technical ground here. We started deep inside the database with the foundational responsibilities of a DBA managing data structures, performance, availability, security. And then we moved out to the complex world of integrating different systems, really digging into troubleshooting APIs, webhooks, and the flow of data between applications.
Yeah, quite the journey from the core data store out to the connections between systems.
So how do these two big areas, database administration and system integration, connect? Why is understanding both of these layers valuable for you, the listener?
Well, they are deeply interconnected in practice. Integrations are very often about moving data between different systems, and those systems almost always rely on underlying databases to store and manage that data. So understanding database fundamentals, how data is structured, how query performance works or doesn't, how availability is maintained, the security implications, all of that directly impacts how reliable and performant your integrations are going to be, especially if those integrations involve heavy database interaction at either end. A slow database can make an integration crawl.
Makes sense. And does knowing about integration challenges help the DBA?
Absolutely. A DBA who understands the common patterns, pressures, and failure modes of API integrations and data flows is much better equipped to anticipate the kinds of demands that will be placed on the database by these integrations. They can design database structures or tune queries specifically to support those integration workloads. And when problems do occur, they're better able to collaborate with integration teams to troubleshoot issues that might originate in an integration layer but manifest as symptoms within the database, like slow queries or locking.
So for you as a listener, understanding both gives you a more complete picture.
Definitely. It gives you a more holistic view of how data moves and is managed in modern IT environments. It helps you appreciate the underlying complexity, communicate more effectively with technical teams working in either database administration or integration development, and potentially diagnose problems that span multiple layers of the application stack, because you understand how the pieces fit together and where failures commonly occur.
This has been incredibly detailed and, I hope, really insightful for everyone listening. We've gone from those absolute core principles of data custodianship, thinking about data structures and normalization, tuning for performance, ensuring availability against all odds, locking down security right through to the dynamic, sometimes chaotic dance of system integrations. We dove deep into API troubleshooting, the crucial role of logs and metrics, and even the specific mechanics of webhooks.
It really underscores the sheer breadth of technical knowledge that's required to build and maintain the reliable digital systems we all depend on today. It's not simple stuff.
It really isn't. Absolutely. As we wrap up this deep dive, it kind of leaves you with this thought, drawing on all the complexity and interconnectedness we've discussed. In a world where data flows constantly, almost like water, between countless diverse systems, is mastering the art of fixing things, whether it's deep within database structures or across the most intricate API handshake, becoming the most valuable technical skill of all.
Hmm. That's a really interesting question to ponder. The ability to diagnose and fix across boundaries.
It's something to consider for sure. Thanks so much for joining us for this deep dive. We hope this journey through the worlds of database administration and system integrations leaves you feeling much better informed and maybe a little more prepared to tackle these challenges yourself.